All right, welcome back. We are going to finish out Chapter 4 of Campbell's Biology. So here we have Concept 4.3. A few chemical groups are key to molecular function. This is an extremely important thing to understand. So let's dive in. So all of the distinctive properties of these organic molecules depend on the carbon skeleton, but also on these chemical groups attached to it. The carbon skeleton itself is fairly inert in that it's not very reactive. It's these other groups attached to it that really make the difference. So let's take a look at how that plays out here. So let's take two compounds, for example. So estradiol and testosterone are both steroids, and they share a common carbon skeleton. Okay, it's in the form of these four fused rings. Both of these are sex hormones. Okay, but they have different functional groups or chemical groups that are attached to it, which makes one a female hormone and one a male hormone. So each one of these things, despite having a common backbone, lead to two very different activities. Let's take a look at them, right? So here we have these four rings, 1, 2, 3, 4. Again, 1, 2, 3, 4. Here we have a pentagon, hexagon, 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 pentagon, hexagon, hexagon, hexagon. Okay. Over here, we even have some similar functional groups attached. So here we have what's called a methyl group. We'll define what each of these are in a minute here. Here's an OH. Here's a major difference. So here we have a CH. Here, instead of being bound to a CH, we have a double bond. Okay. Down here, we have an oxygen with a double bond, and down here we have an OH. You can also see that we have a missing double bond here. This double bond here replaces the double bond that's present over here. So it's really these functional groups or these chemical groups that make the difference in the molecule. So these groups we refer to as functional groups. And we call them functional because it's mostly them that are involved in chemical reactions or weak or strong bonding. So the number and arrangement of these functional groups give each molecule its unique properties. There are 7 of them that you need to know. Okay, so 7 functional groups. Learn these, make flashcards, whatever you need to do, know these groups. Okay. Number 1 is a hydroxyl group. That is simply an oxygen with an attached hydrogen. We have a carbonyl group. That is when you have an oxygen double bound to one of the carbons in the chain. Okay, carbonyl. Now we have something very similarly named. Instead of carbonyl, it's carboxyl group. This is actually a combination of the carbonyl with a hydroxyl already attached, and this gives it some unique properties. We have the amino group, which is nitrogen and 2 bound hydrogens. We have a sulfhydryl group, that's a sulfur with a hydrogen. Okay. Looks very similar here to a hydroxyl, and if you look at sulfur, sulfur is actually the next element down in the periodic table, so it has a very similar valence structure to oxygen. We have a phosphate group, so we have a phosphorus double bound to an oxygen surrounded by other oxygens. This is attached as an entire unit. We have a methyl group, which we've kind of encountered part of before in talking about methane. So here we just have that methane attached to another carbon structure. All right, so let's start off with the hydroxyl group. This is again is an OH, and we may write it forward or backwards based upon how it's attached to, or how a particular thing is represented. Now remember, oxygen is electronegative. This is a polar element, so consequently, you will have a partial negative associated here. You might have a partial positive. This can form hydrogen bonds with water or among other things. This group also has another common name in that it's called an alcohol group. Okay, so when you attach this onto something, you end up with an alcohol. So before we saw ethane, if you replace one of the hydrogens with this OH, it is now ethanol. This is the alcohol present in beer, wine, etc. So the biggest thing here, it's electronegative, so it can form hydrogen bonds. Here we have a carbonyl group, oxygen double bound to one of the carbons. This again is very electronegative and tends to be fairly reactive due to the double bond here. Double bonds, particularly when they're seen with oxygen, tend to be somewhat reactive. Compounds that contain these are called ketones or aldehydes. So if it is in the middle of a carbon chain, it's called a ketone. If it's on the end and attached to that carbon is a hydrogen, it's called an aldehyde. These are very commonly seen in carbohydrates. We'll talk about that in the next chapter. Here we have the carboxyl. Again, this is a combination of the carbonyl with the hydroxyl. This has a unique aspect that with these two electronegative centers, this proton can actually become ionized. And in around pH 7, it would be ionized. So in physiological conditions, we would not see it present like this. It's usually going to be present like this. So you have a carbon double bond to another carbon, and this oxygen is carrying a negative charge, and the proton is lost. Okay? So the fact that you are producing a proton means that it is an acid. This can be a very reactive group. It's also an electronegative center, so it can be involved in all kinds of bonds and chemical reactions. Here we have an amino group. An amino group, that nitrogen has a lone pair. That lone pair of electrons can actually absorb a proton. So consequently, anything that absorbs a proton is called a base. Here, when we look at it, when it absorbs that proton, it'll carry a positive charge. Consequently, it can act as a counterpart to an acetic group. You might recognize the name here, amino, from amino acids. That's because every amino acid has one of these groups. Here we have a sulfhydryl group, more commonly known as a thiol group. I probably will not use this word at all. I always call it a thiol group. Again, sulfur is the next element down from oxygen, so it has a valence of 2. It only needs to pick up 2 electrons to have a full outer shell. Consequently, it behaves somewhat like oxygen, but isn't quite as electronegative. Okay? So it can do things like form hydrogen bonds, but they tend to be a little bit weaker. These thiol groups can also do something unique in that they can react with themselves and form a carbon-sulfur-sulfur-carbon linkage. So this is a unique thing that can happen with this group. We'll address this more in later chapters. All right, phosphate group is a phosphorus surrounded by 4 oxygens. One of those oxygens has a double bond, so looking at this, you might realize that, wait, this has 5 bonds. If you look at phosphorus itself, it should not be able to do that. If you look at nitrogen, which is the next element above, it has a valence of 3. This is forming 5 bonds. If you want to know why, ask me in class. We'll talk about it. This phosphate group is usually added or removed as an entire unit with all of the oxygens. This is something that we use to store energy by linking these onto something else. The removal of it provides energy, or the transfer of this can provide energy. All right, methyl group is just a carbon with 3 hydrogens. We can use this to add a more hydrophobic character onto something. So we can also add it on as part of the process of building longer and longer and longer carbon chains. Methylation has a big impact on genes and how genes are expressed. We'll get into that much later. All right, so looking at all these together again, we have the hydroxyl group or alcohol group. We have the carbonyl. Also, compounds are known as ketones or aldehydes. The carboxyl group, this is acidic. So it releases a proton and has a negative charge after it releases that proton. Amino acts as a base, so it can absorb a proton and become positively charged. Thiol group, these thiol groups can act a lot like hydroxyl groups, but also have the ability to form covalent bonds with other thiol groups. Phosphate group is added or removed. It can provide energy in its removal, but it can also change the surface of another molecule by providing this big electronegative center. Methyl groups can provide a hydrophobic center or just serve as a building block, building one more carbon onto things. All right, ATP. You guys have probably heard of this before. Also known as adenosine triphosphate. So the A is for the adenosine. This is in fact the same A that we see in DNA. We'll get into that in more detail later on. And then you'll see here triphosphate, so it actually has 3 of these phosphate groups. This is how we tend to store energy in our cells in the form of ATP. ATP looks like this. Release of one of these phosphates provides energy. One way to think about it is these are all electronegative groups. They actually have negative charges and they are repelling each other. Sometimes I describe this as, imagine 3 sumo wrestlers playing a game of 3-way tug-of-war. You can imagine that the ropes in between the individuals would be holding a lot of potential energy as they pull on it. This is the same thing is true here. When we break that bond, it releases a lot of energy. That potential energy gets converted to kinetic energy, or more often some type of chemical energy. So when we take ATP, we can react it with oxygen, pop one of these phosphate groups off. That releases a bunch of energy, and that is energy that can be used to do work. So just as a review, versatility of carbon makes us capable of providing a great diversity of different organic compounds, and that variation is largely based, the variation largely depends on the functional groups that we attach to it. So a few chemical groups are key to molecular function. Here we have a difference between these 2 hormones. Here's a listing of all the different things we have out there. And some of these groups can provide energy.